thanks a lot, Vincenzo, for the very long introduction while we were fixing the Zoom. You did an amazing job. So thanks, everybody. It's my pleasure to be here. My name is Jérémie Guillaud. I lead the theoretical research at Alice & Bob. And so I've been quite ambitious with this talk for a very mixed audience, both of general physics, but also experts in qubits and superconducting systems, because they are here at EPFL, some of the European experts in qubits. So I've tried to mix a bit both, give you a general introduction to our architecture, give you some context about what it's good for, how we build it, but I've also tried to give a perspective on the recent progress that we've made both experimentally, so I'll show you the history of the past 4 or 5 years of experiments, and also some recent theoretical results for the experts in the room. Don't hesitate to ask if you have questions. I think the chances that I get through the entire slide are already very low, so if you ask questions, then that's all right, but as Vincenzo mentioned, I'll just have to go in 1 hour, unfortunately. Okay, so a bit of a broad context. So we're trying to build a quantum computer, but for what and why do we not have a quantum computer yet? So here I've taken this picture that kind of summarizes the different types of applications which are envisioned for quantum computing. And they're put on an axis where you have the quality of the hardware, so as a log scale. And usually in our field it's divided, this representation is divided between 2 regimes. The so-called NISQ era for noisy intermediate scale quantum, where you have quantum computers that have typical error rates between 10 to the minus 1 and 10 to the minus 5, let's say. And then this so-called fault-tolerant quantum computing, FTQC regime, where you have much lower error rates. Now the reason why there are so many applications out there that require extremely low error rates is the following. If you take some field of envisioned applications for quantum computing, such as chemistry, finance, or cryptography, and you take a bottom-down approach where you look at the mathematical problem, you look at the quantum algorithms that can solve this problem with an expected speedup, and then compute the number of qubits and the number of gates you would need to run this algorithm on the perfect quantum computers. The typical numbers that you find are usually in these ranges, so you need between hundreds to thousands of perfect qubits, and between 10 to the minus 14 to 10 to the minus, between 10 to the minus 10 quantum gates. And so if your computer isn't perfect but has a finite probability of making an error every time you make 1 gate on a single qubit, then the maximum amount of noise that you can typically tolerate is 1 divided by the number of gates divided by the number of qubits, which gives you those very low numbers in the range of 10 to the minus 13. So now, the typical numbers we have in quantum hardware these days are more in the range of 10 to the minus 3 to 10 to the minus 4 errors per bit per operation. As a comparison, if you look at the classical hardware, so classical RAM, this would rather be in the range of 10 to the minus 25. So this slide is getting a bit old, I guess, because there are now slightly better hardwares with trapped ions, for instance, but still, there are arguably something like 6 to perhaps 10 orders of magnitude difference between the quality of the hardware as it is today and where it needs to be for some of the envisioned application. So I think there are no reasonable physicists that will tell you that we can bridge this gap just by keep improving the quality of the qubits or designing better materials, etc. But it does not mean that it's the end of quantum computing, of course. There is the theory of error correction that addresses this problem. So in a nutshell, the idea of quantum error correction is that delocalization provides protection. So here I'm showing you one of the mainstream approach to quantum error correction, which is to use a quantum error correcting code called the surface code. So the idea is that you'll use many qubits in a 2D array grid of qubits, here depicted by white circles and black circles. And you will encode the quantum information, the algorithmic quantum information, non-locally into this array of qubits. The reason why it helps is that because errors are typically local, spatially local, meaning that the environment will probe the information of a qubit locally, but if you have used entanglement to encode your algorithmic information non-locally, then it gets protected by the typical error mechanisms that you have. So typically, in this array, I encode a single qubit, called a logical qubit, into a surface code using many physical qubits. And the way I can operate this qubit is, for instance, if I want to apply an operator, a Z operator, I will have to act on every qubit along a line in this array. So you can see that this is a non-local operation. This is not something that the environment is likely to do by itself, and therefore the protection. So there are actually two drawbacks to this approach. First, for it to work, you need the quality of the hardware to be below a finite value called the threshold. And so here I'm showing you on the x-axis the quality of the hardware, and here on the y-axis the quality of a single logical qubit. So it's really comparing the quality of a single black dog versus the quality of the full surface code. And so here you have different curves that correspond to different code distances, and you can think of the code distance as just the number of qubits in the code. So usually it's an increasing function, and for the surface code, for instance, the number of physical qubits is the distance squared. And so what you see is that when the quality of the hardware is good enough, so for instance error rates below 1%, then as I increase the number of qubits in the array, so this the curve is going down, then the quality of the logical qubit gets better. And you can actually get arbitrarily better by just making the array sufficiently bigger. So it means experimentally, if I have built a system which I can operate below the threshold, and this is right now where Google is at typically, so they had a very recent Nature paper where they show that they're actually at this crossing point. But as soon as you're below, it just becomes a matter of the size of the system. So let's say I want to run some chemistry application, and I can retro-compute what should be the quality of the hardware. And if I'm below threshold, I can retro-compute the distance of the code, and it gives me the size of the quantum computer. So of course the price you pay is that the number of physical qubits in the physical machine now gets very large if you're just below the threshold. So here is a kind of the same data but plotted differently. So this gives you the number of physical qubits you need to put per logical qubit in the array, given the target logical error rate that you want to achieve, and given how far below threshold you are. So now the axis is the fraction of your physical error rate divided by this threshold value. So again, experimental state of the art is right here today, so a ratio of 1. And in the roadmap of Google, for instance, they envision that quantum computing at scale, while your surface code operated 1 order of magnitude below their threshold. And so this is the typical overhead that they deem reasonable, is to use 1,000 physical qubits per logical qubit. So now if you look at the cost of quantum computing, including this overhead of quantum error correction, you typically find this type of graph. So this is stolen from a recent paper by the Microsoft theoretical research team. So they've taken 4 applications of quantum computing, such as factoring large integers or running some quantum chemistry algorithm. And here you see on the y-axis the number of physical qubits that you need and the time it takes to complete the algorithms for different types of hardware. So either the Majorana qubits that they're trying to build at Microsoft or some superconducting technologies. And so typically if we look at these points here for factoring, then what you see is that you need the quantum algorithms, Shor's algorithm run at scale requires of the order of 10,000 logical qubits. But once you include this 1,000 physical qubit per logical qubit overhead, then it goes into the range of a few millions physical qubit, and this is what you see in this y-axis. So the engineering challenge is a completely different beast, because being able to control such large systems is today still science fiction. So this is the background motivation. Now I'll switch to introducing you cat qubits and more generally bosonic qubits, and try to give you some intuitive understanding of why they can really address this challenge. So the spoiler is really that what we're trying to do is design qubits which are tailored for low overhead error correction. So we'd like to have the same logical error rates, but with much less resources. So the history behind bosonic qubit is to, the idea is to encode information into a quantum harmonic oscillator. So you take, there are different physical realization and for this, and what you typically have are energy eigenstates which are evenly spaced. And so in such a quantum harmonic oscillator, you cannot directly encode a bit of information into the 0-1 subspace because of this equal spacing energy. So what people do when they build transmons, for instance, which are one of the leading, which are the Google qubits, for instance, is that you would make this harmonic oscillator anharmonic by replacing the inductance by some nonlinear inductance. such that the spacing in energy would now become different for each of these transitions, and so you can selectively address and manipulate the information into the 0-1 subspace. The idea of bosonic qubit is different, is to say, okay, we have an infinite, mathematically speaking, we have an infinite dimensional Hilbert space available, so why not try to leverage this resource in order to do some error correction? And so in building bosonic qubits, you have two criteria which make it a good qubit. First, you should choose two states in this infinite dimensional space which have some mathematical interest for error correction. And then you should you should be able in the lab to make a physical physical mechanism that confines the state of the oscillator to remain into this subspace. So right now there are three main candidates for which there are industrial efforts because they are sufficiently mature from both these perspectives. There is the GKP qubit. So the state looks like this, and so in a certain sense it's the optimal way of encoding information in a harmonic oscillator if you have certain error models. And so here I would say it's a mathematically very nice qubit. It's actually been proposed in 2001, so very old qubit. And when it was proposed at the time, I think the most experimentalists deemed it would be a very nice theory construction, but very hard to implement in the lab. And it's been done in the first time in 2019 at ETH Zurich in the group of Jonathan Holmes with the trapped ions. So you know, another nice example where theory is 20 years and it proposes things more like as a nice, nice theoretical object, and then the technology catches up and is able to actually implement those. And now there is an industrial effort to build those at North Quantique in Canada. There is another type of qubit which is not really bosonic but almost bosonic, which is the dual rail qubit. So here the idea in this encoding is that it's much easier to implement. So from the stabilization perspective, it relies on more mature ingredients. And from a quantum information perspective, the interest of that qubit is that if it has an error, it destroys the qubit rather than just preserving the information but corrupting it. It turns out that from an error correction perspective, it's more desirable. And then the last qubit that I will present is the CAT qubit, which has two industrial efforts, to the best of my knowledge, at Alice and Bob in Paris and also at AWS in California. So the mathematical interest of a CAT qubit is that it's a Bayes noise qubit. So you know that once you perform error correction on a qubit, it discretizes the error, and so by linearity of quantum mechanics, you can see that if you are, there are only two types of error to correct for if you want to correct for every type of error that can happen, and those are the bit flip error, which flip the 0 and 1 state. So if your quantum bit is in a state alpha 0 plus beta 1, a bit flip error will switch it to alpha 1 plus beta 0, and the phase flip that will correct the phase of such a superposition. And in many physical platforms, the rate at which those two errors happen are roughly the same. So for instance, for the transpons qubit that I was mentioning, each of these errors happens once every 10 or 100 microseconds in many realizations, or 1 millisecond if you're IBM and you've spent a decade optimizing those systems. But the point is that those errors happen with roughly the same rate. For CAT qubits, the latest numbers we typically have, and I'll show you the experiments, is that the bit flip happens once every 10 seconds, while the phase flip happens once every microsecond. So there are really 7 orders of magnitude between the two timescales with which those errors happen, meaning that for every bit flip we have, on average, we have 10 million phase flips. And as I'll argue from an error correction perspective, it's really desirable to have a qubit where the noise is so polarized, because you can then start thinking of better strategies, since you essentially have a single type of error to correct. Again, just sorry for the physicists in the room, but one thing I mean, the way I like to think of this qubit is almost, it's a quantum bit because I can put it in quantum superposition, but that has essentially classical noise in the sense that I only have one channel of error happening. So before I show you how we realize them and experimental data, I want to give you an intuition of where does this noise bias come from. So typically, so here I'm showing you the Wigner function of the CAT qubit. So it's a mathematical representation in some phase space representation of our computational states. And so we use coherent state of light in a microwave regime, and we encode our qubit. So the logical, the computational 0 state is a coherent state on the right of the phase plane, and the computational 1 is on the left of the phase space. And what happens is that when we pump more energy into our CAT states, those two states get further away in phase space. Now what's important to know is that if in this picture of linear function you look at the coherence mechanism that we have in the lab, they give you a local diffusion in phase space, meaning that, for instance, the main error sources we have in our physical settings are photon loss, where a photon is emitted into the environment. And if I look at the Fokker-Planck equation, it gives me, for the evolution in this abstract mathematical picture, then this will give me essentially local diffusion. And now if I take those two states further away in this phase space, then this local diffusion is very unlikely to make a jump from 0 to 1. And so mathematically, so here it's just like a hand-wavy picture, but you can make this more precise and check that actually, as I increase the size of the cat state, the average photon number, I get an exponential reduction of bit heaps. Now the price I pay is that if I look at the coherent superposition of those two coherent states, so this is where those fringes appear. So this is a cat state. At Alice and Bob we see cats everywhere, so we like to say these are the mustache and these are the legs of the cat, but it's a bit. So then sometimes I forget, we do quantum mechanics. I just Google two-legged cats, and horrible pictures pop up. But anyway, I'm getting sideways here. So anyway, so the point is that if I look at the coherent superposition of these, then as I make the cat larger, then the fringes get thinner, and so the local diffusion I have in phase space is now more likely to blur these fringes. So again, a very hand-wavy picture, but you can make this more rigorous and check that the phase field rate increases linearly with the average photon number. So this is not something we desire. Of course, we'd like the phase field rate to be as small as possible, but the difference in scaling between the way the two types of errors scale is highly favorable. And this is how, with a very small number of photons, we can get a very biased noise qubit. So now for quantum optics experts, how do we stabilize those cat states in the lab? So you know that if you have a harmonic oscillator, which is lossy, and you drive it in resonance, then this will stabilize a coherent state whose complex amplitude is given by the ratio between the amplitude of the drive and the single photon dissipation rate. You can also see this very quickly by just rewriting this piece of dynamics as an effective jump operator of the form annihilation operator minus alpha, and since the coherent state are eigenstates of the annihilation operator, then you can see that the zero of this jump operator is a coherent state. What's nice is that if you, so here you cannot encode a quantum bit of information because the dynamics is just a single pointer state. Now if you square everything up, so if I add and remove photons in pair, engineer this two-photon exchange, two-photon drive squeezing type Hamiltonian, and also a two-photon dissipation operator, then I can again rewrite the effective dynamics as this effective jump operator. And now I will, because x squared equals 1 is an equation that has two roots, I can encode, there are two stable states of these dynamics, which are a coherent state of same amplitude but opposite phase. So now this dynamic stabilizes those two states and actually stabilizes the entire quantum manifold spanned by those two states, which is a quantum bit. So I can encode 1 bit of information there. And you can actually check that, if I were put everything to the power n, then it would give me dynamics with an n-fold degeneracy, and I could encode a qubit into such a system. So how do we engineer those two pieces of dynamics in the lab? So we do everything with this two-photon coupling Hamiltonian. So we have a mode A in which we want to stabilize the cat qubit. We couple it non-linearly to a mode D, which is just an auxiliary mode. So typically it can look like this experimentally. So here you have a top view of a 3D aluminum cavity that will host the electromagnetic mode where the cat qubit lives. And it's and then there is here a mode leaving, which is the mode D. And by applying some pumps, we can basically make this Hamiltonian resonant. Now, once we have this Hamiltonian, by just applying a single photon drive on the buffer, it's converted to a two-photon drive through mixing into this nonlinear element, and then we can engineer also the two-photon loss in this way. So if you're not an expert in superconducting circuits, the moral of this story is the following. So we need some exotic Hamiltonian for the cat qubit to work. And the way we do things in superconducting circuits is always the same. We have a single nonlinear, non-dissipative element in superconducting circuits, which is the Josephson junction. And then we try to implement effective Hamiltonians by just making some devices which contain these junctions and applying pumps at well-chosen frequencies. The goal being that the effective Hamiltonian of the system is very close to the one we desire, without inducing other spurious terms that will then result in just more errors on the qubit. Okay, so that was the end of the technical part for the superconducting circuit people in the room. Now I'll switch to a more historical background of what we've been doing in the past 4 years and the experimental realization of this cat qubit and the exponential bit flip suppression. So I'm actually telling just the end of the story. It all started at Yale University in Michel Dovreu's group by many people there, and then it was picked up by Zaki Lektas, who did a postdoc in Michel Dovreu's group, was the first person to stabilize cat qubits in his group. And then he came back to Paris at ENS as a professor and started, kept doing this research program. And his first PhD student, Raphaël Lescan, then became one of the co-founders of Eisenberg. So there is really like a complete historical legacy from academia to industry. And so the first experiment they made in Paris, which was the first experiment that demonstrated the exponential suppression of bit flips in a cat qubit, was done in 2019. And here are the results. So what you see here is the bit flip lifetime of a cat qubit as a function of the average photon number. And what you should notice is that the Y scale here is in log scale. So if you have a straight line, it means that you have an exponential suppression of bit flips. And in this cat qubit, for each added photon, the lifetime of the bit flip lifetime was multiplied by 4. Now, on the other hand, you can also look at the phase flip rate, and as expected by theory, when you increase the average photon number, the phase flip rate increases linearly. Notice the linear scale. And so what's interesting in this plot is that according to theory, you should have an exponential suppression of bit flips that never ends. And here in this experiment, there was a saturation of bit flip around 1 millisecond. So what it tells us about the system is that there is a physical error mechanism happening in the lab that induces non-local jumps in a phase space at a rate which is roughly 1 millisecond. And the reason is, I was arguing that in the Wigner representation, the typical error mechanisms we have induce local diffusion. Then when you see this, it cannot be local, otherwise it would be exponentially suppressed. So it was understood in this experiment that this non-local source of errors came from the transmon that was used for the readout. So I've shown you the Wigner of the cat qubit, saying it's an abstract mathematical object, but this is actually the function we measure in the lab when we want to tomography the quantum state. And for this, we need to couple a system to it that allows us to actually measure those Wigners. And here it was understood that, so here it's a dispersion plotting. It's a very standard way of measuring linear functions in superconducting circuits. But it was understood that when because the transmon had some finite temperature, when it picked up the thermal excitation, it was inducing a detuning on the cat qubit, which was opening a channel where the cat was rotating in phase space. And if you do, so in this paper they did the math, and they realized that with the temperature measured of the transmon, it was consistent with saturation of bit flips around 1 millisecond. So next experiment that was done was to check that indeed it was the case that the transmon was causing this saturation, and so they removed the transmon and did the same experiment. Now the problem if you remove the transmon is that you lose your tomography apparatus. So you may have a successful experiment, but you're not able to measure the quantum state, so you cannot really see the results of the experiment. So it took a bit of a while to devise another non-invasive way of observing bit flips in this circuit, but just without the transmon. And so that was done and published in last year. And so what they observed is now an exponential suppression of bit flips over almost 5 orders of magnitude, up to a bit flip time of 127 microseconds, where it saturates again. So so basically there is a main drawback with this experiment, is that they were not able to tomography completely the quantum state. So we cannot say that this is a qubit, and actually this was vividly debated in the field. But what it tells us is that structurally, in the circuit that we use to stabilize cats, there is no non-local physics happening causing a bit flip between a rate of 1 millisecond, where it was, up to 2 minutes. And now you may wonder, what is the source of this saturation at 2 minutes? It tells you that again here you have another physical phenomena that's inducing non-local jumps. And this is still under investigation at the moment, actually. One of the main suspects is the effect of high energy particles coming from cosmic events. Another less sexy reason could be just the fact that, these are very long experiments over which we have slow drifts of some experimental parameters. Like typical experiments, you just last a few milliseconds. Here, it's really traces taken over a few hours where external parameters are shifting, and such that we could lose at some point the protection.
Jérémie, can I ask a very silly question? Why the convention is to encode the bit flip in this degree of freedom and not the phase flip? So why does one encode 0 and 1 on the two coherent states instead of encoding them in the two cat states? Is there a technical reason? There should be no.
No. So originally it was the other convention in the theory, and also I know at Yale theorists and experimentalists do not use the same convention.
Okay.
I switched conventions in 2019 when we were building the architecture for CAT. So we were finding how to do gates on CAT qubits, and then how to assemble them to have a universal set of logical gates. And one of the gates we found that was non-Clifford and allowing, that was the trick, had no name in the literature. So I was very happy. I called it the Mirai gate for my PhD advisor's name. And then we realized that if we Hadamard this gate, it was just a Toffoli gate. So we decided to switch bases
okay.
just to have, but it's really like a theorist reason that we don't have an attachment. If you ask Michel Devoret, he'll give you very strong physical reasons why it should be this or this basis, but for us it's just... Anyway, so back at where we were. So once we had this experiment, first we were quite happy because you have very long bit flips. But of course, you want to be able to do what you could do previously, which is completely perform a quantum tomography of the state to check that it's an actual qubit. And so this was done very recently. So the paper was put on the archive last July, and will appear in a journal very soon. And so in this experiment, what you see are 3 different cats, which, as you can see, are bigger and bigger. So this is really experimental data. Here you have a cut of the Wigner where you see the fringes getting thinner as promised, and the most interesting is the decay of the logical X and Z operators of a cat qubit. And as you can see, when you increase the photon number, the phase flip time decreases linearly, and the bit flip time increases exponentially. And what's really nice is that now you're able to have both lifetimes, and so this is where typically the numbers I was quoting at the beginning come from. So those 7 orders of magnitude difference between phase flips and bit flips. Here for experts, what took so long in doing this experiment is that since we didn't have the transmon to tomography the state, we had to implement another way of measuring the Wigner function. And this was done essentially using the nonlinearity, the same nonlinearity that is used to stabilize the cat state. So the cat mode is coupled to a circuit containing Josephson junctions, and this nonlinearity gives you a universal control over the mode. So there is a way to map the parity of a cat state onto a system that you can measure, and this is how we get these nice Wigners. Okay, so I think I'm halfway through. I do have an extra thing I think I can show. So these are results that are not published yet. We've shown them at the March meeting, and it should come soon. But I wanted to show you this because it was theoretically proposed by Vincenzo Savona and David Schlegel here at EPFL. And the idea is to use the squeeze cat. So in this picture, you see that when you increase the average photon number, you're very happy because you get these very long bit flip times. But the phase flip decreases linearly. And this will become a problem once we put cat qubits into an error correcting code, because these are the errors that you need to correct for, and even a linear decrease, when experimentally you're so close to the threshold. I was arguing that Google is now at threshold after 10 years of brute force engineering, so the factor 2 here actually mattered, and this linear decrease might be a problem. So the solution that was proposed theoretically in Vincenzo Savona's group is to use squeeze cats, and basically again, hand-wavy explanation is that to take a cat, and the cat lives in a circle which gives you roughly the average photon number, so you don't want to go out of that circle because this is where your phase flip starts decreasing linearly, but you can still increase the distance in phase space between the two states that give you the exponential suppression of bit flips by just squeezing the cat within this circle. So again, the theory was first proposed here at EPFL, then it caught the attention of cat qubit community very quickly, so there were many follow-up theoretical papers, and there were previously some experiments that were done that have been achieved both in photonics platform and superconducting circuits to just prepare those squeeze states, but never to really stabilize them. To stabilize and again, I think if you want to, so I'll just flashily brief a couple of results, but if you want to know more, I think the talks of March meeting are still available online. It's like 90 days, so I am putting the references so you can have really the full talk. The way you can stabilize the squeeze cats versus instead of regular cats is just by squeezing this operator. So remember I told you that you can stabilize cat with this nonlinear dissipation, which comes from this Hamiltonian here and some dissipation on the buffer mode. It gives you a nice cat. Now if I just squeeze this dissipation operator, then it gives me this, I need to implement this jump operator, which is developing this one. And basically it's exactly the same as before, but you have additional terms in blue here, which are other effective Hamiltonians I need to engineer. And now if I'm able to engineer all those terms, then this will stabilize cat state. And remember here, the recipe is always the same as with other superconducting circuits. I need additional Hamiltonian terms, so I'll just think of a device containing nonlinearities and then apply pumps at some well-chosen frequencies, and this should squeeze the cat. Now for experimentalists, when you look closely at this Hamiltonian, you know, this term is a high frequency term, it's not desirable for some reason. And what's interesting is that you can actually remove it. So if you just remove this term, then you get this jump operator. And what it stabilizes is not really a squeeze cat. It's a squeeze cat which has a kind of a moon shape going inside. So we've called that the moon cat. You know, we're not very inventive with names. But the point is that if you make some theory simulation and look at the bit flip rate by increasing the average photon number of both a moon cat and a squeeze cat, so here there are two curves, dotted curves and plane lines, then you can see that basically they are the same. So the enhancement in, I mean, you know, from that intuitive picture of squeezing a cat into a circle, you can kind of understand why this moon cat will be also nice. And then, so this is again the linear increase in phase flips with respect to squeezing.
You should call it the croissant cat. You have the best croissant in the world there where you are.
I'll suggest that internally. Okay, so this is an experiment that was done. I'm just flashing you the experimental setup, but I'm not an experimentalist, so I just think that, so basically we're using a low frequency cat, and to make the cat low frequency, we need a big capacitance, and the way they found to make a big capacitance is to use this kind of fractal shape. You know, fractal are known to maximize the perimeter in a fixed area, and it works well. So I think, you know, first they show me the design that I think they were making fun of theorists, but then they were like, no, we're actually building this, and it works. But anyways, and then so the experiment was conducted, and this is so a measured Wigner of a moon cat, and you can see, I hope you do see the moon shape. And you know, when I never get tired of Wigner of cats. And trust me, this one is much nicer looking than the one we typically have internally when they do things quick and dirty. And then say, oh, it's a moon cat. There are like 4 pixels in the picture. And now I think this is convincing. I mean, anyway, so now this is again the measured bit flip exponential suppression as a function of the cat size. And here what I'm showing is just the coefficient in the exponential suppression. So this is for a factor lambda of 0, meaning it's just regular regular cat without squeezing. And then as you increase the kind of generalized squeezing parameters, you see that the exponential suppression of bit flips gets faster. Here you have the phase flip as a function of cat size. So in theory, all those curves should be superposed. We do understand why there is a small deviation, but I don't have the time to get into the details. And the point is just that with a cat size of about 4 photons, we can reach a very good bit flip time, and the phase flip time is now slightly higher. So you know, I'm not trying to fit this to theory and show you that without the squeezing, I mean, this is as good as it should be. This is ongoing experiment, unpublished results yet. Still, we do have this enhancement and can reach a very nice noise bias, so 6 orders of magnitude here with only an average photon number of 4, when in the previous experiment I was showing you it was with 11 photons, so we almost divided by 3 the number of photons. Okay, so now for the rest I'll switch more to I want to discuss a bit the rest of the architecture. Once we have these very noise bias qubits, what do we do with them? What does the architecture look like? And then comment a bit on theory result. So one thing I want to come back is justify the name of hardware efficient protection against bit flips. And usually the way I like to present cat qubits is that they are a hardware efficient repetition code. So to justify that, let's assume you start with a qubit that has the same probability to have bit flips and phase flips, and you embed this qubit into a repetition code against bit flips. So what you would do, it's a bit the analogous of the surface code, but not just to correct one type of error. So what you would do is use a 1D line of qubit and call your logical 0 the tensor product of all of the qubits being in 0, and logical 1 the tensor product of all the qubits being in 1. Now, if you want to induce a logical bit flip on this logical qubit, then you need a majority of the physical qubits to have a bit flip. Now, if the bit flips are independent and small with respect to 1, to leading order, this happens when you have a majority of the qubit that have flip, and so it happens with the probability proportional to the physical probability of having a bit flips to the power d/2. So as you increase the distance of the code, the number of qubits in the line, this goes exponentially to 0. Now, if you look at the other error, it's just so the logical error is when you have a flip of the sign of this logical superposition, then you realize that any physical phase flip on those qubits will put a minus sign in front of the tensor product, and so any physical phase flip will induce a logical phase flip. So if you have, again, independent errors, then the probability that this happens when you increase the distance of the code is linearly increasing with the number of qubits. So I like to say that cat qubits are kind of a hardware efficient repetition code because you have the same type of scalings in the two types of error. Whereas, but the thing is, it's hardware efficient because in the case of cat qubit, all you have to do is to increase the average photon number, which is really increasing the amplitude of a pump of a drive in the laboratory. So just turning a button higher and higher while having the same hardware. Whereas in the other case, you have to put more and more physical qubits on the chip. So you really have to increase the size of the hardware. And so I like to put, the experiment that I was presenting you, where you increase the average photon number and look at the saturation, in perspective with the experiment that Google did 2 years ago, where so on this Sycamore chip, they also implemented a repetition code. So they're at threshold for the surface code, but the threshold of the repetition code is higher. So it means they're below the threshold of the repetition code, and so they could check experimentally that by implementing a snake shape just to make it fit on their grid, but a long repetition code, they were able to suppress exponentially the logical error of one type of error because it's a repetition code. And so what they see is the dark blue dots here is that as they increase the number of qubits, which is the analogous of the photon number, there is a nice exponential suppression of the type of error they choose to correct. So let's say, for instance, bit flips. And what I think is nice is that also in their experiment, they witness that at some point it saturates. So here around a rate that would correspond to 1 second. And what it tells us really is that at this rate, there is a physical error mechanism happening on the array of qubit, which is non-local. Because again, as an introduction, I was saying the surface code works because the errors are local on the qubits. But if you have a physical mechanism, physical error that happens, and all of the qubits suffer from an error at the same time, then this spatial delocalization is not going to protect you. So in this experiment, it was understood that it was due to high energy events, due to cosmic rays. And what was very convincing is that if they post-selected, on the trajectories where this did not happen, then they recovered a nice exponential suppression up to lower.
You say repetition codes have a high threshold, but starting from which length? Because I thought the small repetition codes have a.
The notion of the threshold is anyway defined in the limit of infinite size code. Yeah. When you look at small instances, you have finite border arrays effect, and so actually in the Google paper, they improved their system up until the point where the distance 5 surface code, which is here, outperformed distance 3. So they have a figure in the paper where they show all the points of previous version of their experiment, and they decided to publish in Nature when this point got below this one. But they are very honest about the fact that it doesn't mean they are below the threshold of the surface code. It's really just because there are finite boundaries effect that here distance 5 is better than distance 3. But if they kept increasing the distance, eventually those black dots would have come back up. But it's really kind of a detail. So anyway, so how do we move to now a perfect logical qubit? Well, if you have a cat qubit with a huge noise bias, then you can think of tailored strategies. So here I'm showing 3 different examples in the literature on how to tailor a surface code to account for the fact that you have a noise bias. So either modifying the stabilizers using a thin rectangular surface code or a locally deformed version of the surface code like the XGX code. And what we do at Alice and Bob, at least for now, is to just rely on the exponential suppression of bit flips due to the large photon number to correct for bit flips, and then only use a classical code to correct for phase flips. So what we proposed and what we're doing right now is to put the cat qubits in a repetition code correcting against phase flips. So it's really a kind of a concatenated architecture where each of the cat here is a kind of a hardware efficient repetition code against bit flips, and then the outer code corrects for the other error. And so this object now is a proper, fully protected quantum logical bits against both phase flips and bit flips. So one of the questions we answered at the time is, can you operate this qubit in a universal manner? And the answer is yes. So here is the, just flashing the architecture. So in this gray box here, you have the toolbox of all of the physical gates we know to engineer on cat qubits. And what's really important is that these gates should be bias preserving, meaning that they should not depolarize the noise. For instance, there is a very simple reason for which the Hadamard gate cannot be in this set, because assume you apply a Hadamard gate on the cat qubit, this will have 2 effects. It will process the logical information encoded in the cat qubit by applying Hadamard, which is what you want, but it will also apply the Hadamard gate on whatever errors were happening on the qubit. So if you had a phase flip error on the qubit just before the gate, then after the gate, you've both performed a Hadamard, but also converted the noise to a X-type noise. So you're reintroducing bit flips at the highest dominant rate which exists in the system, which is here phase flips. So this is not something we want. And so what we've done with this architecture is to show how at the logical level, so at the level of the repetition code made of cats, you can still have a universal set of gates while using only bias preserving operations. Okay, so I'm getting to the last part of the talk, so now I'm completely switching gears. So I want to, so just a bit of context. We first built this architecture proposing repetition codes on cats because we knew nothing about error correction. And so when you know nothing, the easiest code to understand is the repetition code, and it's also very easy to implement experimentally because it's only nearest neighbor interactions on the 1D line of qubits. It has a high threshold. I mean, it makes a lot of sense to start experimentally by this one. But now it is known, classical error correction has been around for more than 50 years. It's not used for computing because the hardware is satisfying enough, as I was mentioning in introduction, but it's been developed for communications, for instance, when you have to send bits to a satellite, they arrive corrupted, or even in a lot of technologies like Wi-Fi or 5Gs, there are classical error correcting code that correct errors at the output of the communication channels. So, since what we need is classical error correction, it's very tempting to draw inspiration from all of this research. And one class of code which is very promising these days is LDPC codes, which are actually codes that are used in 5G, for instance, where LDPC stands for low density parity check. Now, when you take a classical code and want to use it in a quantum framework, there are 2 things that are highly non-trivial. The first one is that usually for classical code, everything is done in software, meaning you can check the bits. There is the measurement back action of quantum mechanics, so you can compute directly, read out your bits, and then do some processing offline. And so the codes that are typically built are highly non-local, so you have checks on many bits. And the other thing is that here we want to compute on those codes, which is not something that is done classically. So classically, the only thing they want to do is to preserve the information through a communication channel, but here we want to be able to actually manipulate the encoded information to perform a computation without having to decode the information, process and re-encode, which would not protect you against the errors. So I'm just flashing here the results. So here, I'm showing you numbers of number of physical qubits you need per logical qubit in order to encode 100 logical qubits, assuming you have a physical noise of 10 to the minus 3, which is close to what we have in experiments today, and assuming your target logical error rate is 10 to the minus 8. So assume you have like 100 million gate algorithm to run on 100 logical qubit. This is what you would want to have. And here there are also 4 main architectures. So the first one is the surface code with superconducting circuits qubits, like the approach of Google. And here you will need, in order to implement that 100 logical qubits, 33,000 physical qubits. So it roughly splits as, if you want to go from a physical error rate of 10 to the minus 3 to 10 to the minus 8, then you need a code of distance 13. So in your array, you have a 13 by 13 qubits, it's 169. And if you double that number for the NCLAS, it's 337 physical qubits in that array. And now if you want 100 logical qubits, then you need to replicate 100 patches. And so this is how you come up with 33,000 qubits. Now those LDPC codes are a very hot topic in theory right now. And so last summer there was a paper by IBM showing you how you can implement small instances of quantum LDPC codes. And what they found is that to achieve the same performance, they need roughly 2,000 physical qubits, which is a reduction of a factor 14 of the number of physical qubits. And it's roughly the same as our architecture where we put cat qubits in LDPC codes. So this was the state of the art, last summer. And when we saw this, what's very tempting is, to put cat qubits and put them into LDPC codes, so that we have both optimized somehow the bosonic error correction layer where we suppress bit flips, but now also the higher level with denser LDPC codes. And so what we find is that we need 700 cat in the end, including ancilla qubits, to implement 100 logical qubits. Now, when you think about it, it's all of this is theory, right? So we have yet to build that chip, but when you think about it, the number of data qubits you have in this number is roughly 400. So it means that you can encode 100 logical qubits with distance 22 into 400 data qubits. So the overhead of error correction is now only 4 to 1. So 4 physical qubits per logical qubit. When in the roadmap with surface code and superconducting qubits, you need roughly 1,000 physical qubits per logical qubit. So it's a huge reduction in the overhead. And so this is how, in the end, we think there is a path forward.
Is this fault-tolerant?
Yes. So here is just a code. So this is those numbers just to preserve. But then you can do gates.
But the question is this high rate LDPC code with cat qubits. Is it going to have a universal set?
Yes.
Of gates?
So here it's actually just we've just copy pasted the architecture for repetition code. So it's described in the paper, which is here, and. But I don't think I'll have time to go into this. So I want to draw your attention to an interesting fact we discovered when making this project with LDPC codes, is the fact that, so those of you that have heard of LDPC codes will know that usually people say, oh, LDPC codes are nice, but we need long-range we need all-to-all connectivity or long-range connection in the processors to make it happen. So that it's better suited, for instance, to architectures where you have such long-range connections, like trap ions, for instance. And this comes from a theoretical result called the BTP bound for Bravi, Terral, and Poulin, famous theorists in the field of error correction. And so it says that if you have a quantum code that is local in 2D, then you have a strong upper bound on the performance of the code. So assume you have a code which encodes k logical qubit of distance d into a number n of physical qubit. So the bound says that if your code is 2D local, then kd squared has to be cannot grow faster than the number of qubits. So this is for a family of codes where I'm increasing the number of physical qubits, and it's giving me codes with parameters, like the surface code, for instance. The surface code, I can increase the size of the patch. It gives rise to a family of codes of increasing distance. And basically, the surface code saturates this bound. So for the surface code, in a single patch, the number of encoded qubits is k equal 1. The distance is square root of n. And so if you compute that number, it's already growing linearly with n. And actually, there is, in this theorem, there is more than just this bound. There is the prefactor, which is code dependent. And when you compute it for the surface code, you see that it saturates this bound quite tightly. So it means that if you want to do a surface code that is a quantum code that is local in 2D, then you cannot hope to achieve a better performance than the surface code. And the surface code, as we've just seen, has a rather poor encoding rate. So usually when people build LDPC codes that are local, that are in 2D, because this is desirable from an experimental perspective, you necessarily have to go to long distance connections. And so for instance, if you look at the LDPC codes built by IBM that I was flashing, the layout that they propose is the following. So you have this grid of qubits with some ancillas and datas. And so you have those nearest neighbor connection as you would for a surface code. And then the additional connection you need are those lines. And so here they only shown one to not make it a mess. But the actual code is this one where those connections are reproduced by translation vertically and horizontally. So if you picture, the layout, it's like a massive. There are connections everywhere, and this is how they got to their codes that have a higher encoding rate than the surface code. Now, what is nice is that if you look at the same version of the mathematical theorem for classical codes, then the repetition code saturates the bound in 1D. But it does not saturate the bound in 2D. So in 2D, the bound looks like this. So it's k times square root of d cannot grow faster than linear in n. And for a repetition code, we encode one logical qubit into n physical qubit. But so you can check if you plug this here that there is room for improvement. So you can encode more logical qubits. So what we've done, based on this insight, is just start by plotting a grid of qubit, and then brute force every possible stabilizer shape while keeping local stabilizers, because we know it's experimentally desirable. And what we found is plotted in this graph. So here in this graph, every symbol you see is a different code. And you see in the x-axis the code distance, on the y-axis the factor kd divided by n. So this is relevant because for a repetition code, kd over n is equal to 1 by definition. So the k equals 1 and d equals n. And so basically when you see a code, for instance, that has a value kd over n equal to 3, it tells you that for the same distance as the repetition code, you encode 3 times more logical qubits. So we want codes that are higher in this y-axis. And then here, what we show is the stabilizer weight. And so stabilizer weight is really the number of qubits on which each check is acting. So from a technological perspective, is really just the number of nearest neighbor connections. So of course, you want this number to be as low as possible. And for instance, the family of repetition code is here, where you have stabilizers of weight 2 because it's just nearest neighbor checks. So anyways, we were quite happy to see that actually, when we did a brute force search for codes, almost all of the codes we found were better than the repetition code, which was our architecture. So it's a bit shocking to realize that it's not hard to build good codes. And then we just had to pick some compromise. So I think weight 4, for instance, is a nice compromise. So this family of, these green codes are nice because they have the same technological constraint as the surface code. So it's 2D local and weight 4. Yet you can have much higher encoding rates than the repetition code. Okay, I have to leave in 5 minutes, so I'll just switch to conclusions so you can at least have the chance to ask one question. I think the rest is not so interesting anyways. I just want to show you as a conclusion, this is a bit what and also to answer Vincenzo's question, this is the layout we have in mind. So here you have a layer that contains the LDPC code qubit. So this is not at scale, but all of the qubits are here. So this is really what a processor with 100 logical qubits would look like, with a logical error rate of 10 to the minus 8, on which you can perform a universal set of logical gates, which you can do with this architecture. So this would be a flip chip. This is typically, in total in this architecture, you have a bit more than 1,000 qubits, so 700 in the upper layer, 700 in the lower layer. And the chip will be 8 centimeters wide. This is exactly
almost analogous to the largest chip that IBM has been releasing last November. So it's a 1,000 qubit chip, a few centimeters wide, and so it's very reasonable. Again, I'm a theorist here. If the experimentalists were listening to me, they would kill me. But from my perspective, this is a reasonable object to build in the coming years. And and when I tell algorithmic people that they have 100 logical qubit operated at 10 to the minus 8, then they get interested. This is unarguably beyond the NICS regime, and so there might be some applications with this thing. I must stress that there are hypotheses behind those numbers. Those hypotheses have not been realized experimentally. Also, I mean, there is a long way ahead. But anyway, this is where we're heading at. And so yeah, with that, I'd like to thank you. I hope I've convinced you that cat qubits are a way to low overhead quantum error correction. And here I'm flashing. So I've tried to give you current experimental challenges, squeeze cats, and also I haven't talked about the bias preserving CNOT gate. There is also a talk online that you can watch, and then some recent theory improvements. Thanks.
Jérémie, the next 2-minute question. Alexander, who's
I don't want to steal the only question, so I'll try to be brief. But it's always hard to compare between Hamiltonian stabilization and dissipated confinement, but there's some kind of duality between Kerr-Cat and two-photon dissipation. Now, when I look at the moon kit, I see this A-dagger A in the dissipator, and I wonder if the Hamiltonian dual to that would be a detuning. Is there some connection between a detuned Kerr-Cat and the moon kit?
That's a tough one. I'm not sure. I mean, we can discuss, but I would not answer that recorded because I might say something stupid.
1-minute question.
Sure.
So there was this table where you showed the number of logical qubits without and with the IDPC codes. So I was wondering, for the case with the cat qubit, does this thing also then depend on the size of the cat?
Yes, so here the goal is to reach a logical error rate of 10 to the minus 8. So what you do is find the size of the cat that gives you the right bit flip. And the right bit flip is actually 13 minutes in this case, meaning which you reach for a certain average photon number.
Talk about